All right, so I want to do a few more examples with universal law of gravitation. So let's look at a second example, and we'll keep this example short. We just want to find the force due to gravity for normal sized objects. Okay, so let's just say we have two objects. We'll say object one has mass of 2 kilogram. We'll say object two has a mass of 5 kilogram. I'm just kind of making up numbers for this. And we'll say that their distance is, we'll go with 1 meter. So they're 1 meter apart. And we want to find how much force they are pulling on each other with. So if I plug those into this formula, we have big G m1 m2 over r squared. Big G again is 6.67 times that by 10 to the negative 11. That's a Newton meter squared per kilogram squared. Okay, and then plug in those masses. So we have 2 kilogram times that by 5 kilogram, and then we're going to divide by 1 meter squared, which is still 1 meter. All right, so let's go ahead and plug that into our calculator. So we have big G times that by 10 divided by 1. So I'm getting 6.67 times 10 to the negative 10 Newton. Okay, that's a really small force. So compared to normal forces that we deal with, that's really small. So we basically ignore the gravitational force between two normal sized objects because it's not going to change our number until you get to the 10th decimal place, basically. So one more thing we could do with that is just find the acceleration for one of them. And so that would be force over mass. So let's find the acceleration of the smaller object, mass 1. So A1 is going to be force over M1. So that'll be 6.67 times that by 10 to the negative 10. Divide that by the mass, so 2 kilogram. And so that'll be about 3.3 times 10 to the negative 10 meter per second squared. So basically no acceleration. You'd have to be, in order to observe this, you'd have to be far enough away from any other objects out in space, no air resistance, in order to see anything happen. So we don't really use universal gravitation for normal sized objects. It doesn't really make sense. All right. Let's look at another example here. So this would be example 3. And we're going to talk about gravitational field. So gravitational field. Okay, so let's say, for example, if we have the Earth or any object. So here's our Earth. We know that if something is near Earth, is going to be pulled towards the Earth, right? And so there is a gravitational field around Earth. We can imagine some field lines here around Earth. And if something with mass is near Earth, then it is going to be pulled in the direction of the gravitational field. Okay, and gravitational field is it's kind of like force, but it's the force per mass in that gravitational field. So if we think about, let's say, a satellite orbiting Earth with mass m, we don't want to know the force on that mass, but we'd like to know how some mass would be affected by Earth if it were near Earth. Okay, and so basically what we're looking at is the force due to gravity per mass m. And if I plug that into the gravitational universal law of gravitational force formula, we have big G mass of Earth times some mass m over r squared, and then divide that by the mass m. Then that cancels out this mass right here, and we end up with gravitational field of Earth is big G mass of Earth over r squared. Okay, and you can do this for any object, but we define the gravitational field as little g. So we have little g is equal to big G. For Earth, it'd be mass of Earth over r squared. And then what I want to do with this is let's find the gravitational field for points that are really close to Earth. Okay, so if we imagine this satellite is some distance away from the surface of Earth, we'll call this D. Okay, and we're looking at any scenario where the distance is much less than the radius of Earth. So we're really close to Earth. And I want to find the gravitational field when an object is that close. And if I do that, then we're going to use, so in general, gravitational field formula is going to be Gm over r squared. But I'm going to use the mass of the Earth for mass, and I'm going to use the radius of Earth for the distance because we're really close to the surface. Let's go ahead and plug in some numbers and see what we get. So G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. We have the mass of Earth. Mass of Earth is 5.97 times that by 10 to the 24 kilogram. And then we are dividing this by the radius of Earth squared, which is equal to 6.38 times 10 to the 6 meter. And we're going to square that. All right, so plug those into our calculator. And if you do that, I'm getting about 9.8, rounded to the nearest decimal, 9.8. And the units for that would be if you look at our formula here for gravitational field, we took a force and divided it by a mass, so that would be a Newton per kilogram. And hopefully this reminds you of another number. This is equal to the acceleration due to gravity on Earth. Acceleration due to gravity on Earth. And so when you find gravitational fields caused by some object, let's say the Earth, or it could be any object, the moon, the sun, Mars, whatever you want, what you're really finding is the acceleration for an object that would be located at that given point, some distance r away from the planet. All right, so another way to get 9.8 is through that formula. So that's it for gravitational field. I have one more example for you to try for yourself. So fourth example, I want you to try this, and then I will post the solution for it. So the first example that we did, we found a few things for Earth and the moon. We found the force due to gravity on the moon. We found its acceleration, its velocity, and then its orbital period. And I want you to try the same thing, the same exact problem, but for the Earth orbiting the sun. Okay, so for this problem, we want to find force due to gravity. We want to find the acceleration due to, the acceleration of Earth from the sun, which we just learned is basically the same thing as little g, right? But for the sun, some distance away from the sun. We want to find the velocity of Earth orbiting the sun, and we want to find its orbital period in days so that we can hopefully get really close to 365 days for the Earth. And again, for these problems, we are assuming a circular orbit. And so let me go ahead and give you some values for this. Mass of the sun, call it MS, is equal to 1.99 times 10 to the 30 kilogram. The distance from the center of mass of the sun to the center of mass of Earth, this would be an average distance, is 1.5 times 10 to the 11 meter. And then I'll go ahead and write down again the mass of the Earth for you. So mass of the Earth is equal to 5.97 times 10 to the 24 kilogram. So go ahead and try to figure out those values, and then I will post the solution for it later.